Okay. Yeah. You don't need to do much, but here they are. All right.
All right, and if we could settle down, we'll get started with our next talk with Kristoffer Carlsson, Tim Holy, and Sebastian Pfitzner.
Okay, good morning, everyone. We're doing the daring and crazy thing of 3 separate presenters and 3 separate laptops in one talk, but that's in part because of the way we've decided to structure this. So we're going to talk about some very collaborative work that we did recently, and building on some work by others even in the room, developing new tools for debugging your Julia code. And for me, personally, this was an immensely fun, and remains an immensely fun collaboration among the 3 of us. We're also doing the presentation in a very collaborative sense. In particular, I want to caution you against assuming that if I say something, that means I did it. I'm actually talking about their work in some cases, and other people's work as well. So we're just trying to sort of give something, sharing out the pleasure of trying to give something useful to the community without worrying too much about micromanaging credit here. So anyway, without further ado, let me sort of plunge into it. I don't want to make the assumption that I bet most of the people in this room know what a debugger is, but I actually don't even want to assume that. So let me sort of begin by a very sort of general issue, and that is that most of you who write Julia code probably have once or twice at least had a bug in your code, and you want to be able to find why something doesn't work quite as well as you would, or even if you just want to understand what's going on internally a little bit more. One of what I would say is actually the most powerful feature of Julia for debugging is its command line interface, right? And so if you have a function that you're running and it throws some kind of error and you might want to understand what does that, the trick probably most of you use is to essentially, sort of define some variables that have the values that were being passed into it with the same names, and you can copy and paste the source code into the Julia prompt, and you can sort of figure out why you got some error from the square root in that function, for example, okay? So this is incredibly powerful. I use it all the time still to this day, even with other tools available. But in certain circumstances, at least, it can get quite tedious, because if you have a top-level function that calls other functions, which call other functions, and you don't always know which ones those are, sort of tracing the whole thing down, knowing which code you should be copy-pasting into your command line, can take quite a long time. And so the obvious question is, since computers should work for people rather than vice versa, can one write tools that help with this process? And so that general category of tool that helps with this is called a debugger. And over the years in which many different languages have implemented debuggers, there's sort of a standard feature set that's been arrived at, right? So, one of them, which, we saw just from the command line prompt, is you want to be able to inspect the values of local variables, but you want to be able to, for instance, step forward in code one line at a time. You want to be able to dive into the functions that get called by your code. You want to be able to get back out once you've dived down deep to go back up to higher levels. And then finally, you'd like to be able to run a block of code without interruption, maybe until you get to either it finishes or there's an error, or you insert something called a breakpoint, which is a manual stop that you've said, please stop here. And those can be either sort of unconditional or conditional, meaning they might only happen under certain circumstances. So this is sort of the core functionality that most debuggers should implement. Now, one of the really fascinating things about Julia is that the code that you write, which is at the top level of that diagram up there, undergoes many, many separate stages of transformation on its way to machine code, which is the thing that's sitting at the bottom of this hierarchy. And this provides many opportunities to scratch your head and wonder at which level should you target for writing a debugger. And perhaps unsurprisingly, over Julia's history, therefore, there have been several projects writing debuggers, and they have actually targeted different levels of this hierarchy. So the oldest of these is a debugger called debug.jl. It was written by Toivo Henningsen. It appeared within sort of a few months of Julia sort of bursting out onto the public scene, and it was a wonderful tool at the time. So I'm showing you some of the syntax that package had, and I think the reason that we're not all using debug.jl today is for one important reason, and that is that you had to actually modify the code that you wanted to debug. in order to use it. So you had to open your code up in an editor, modify it, and then that would trigger the debugging. And this was also before we had the ability to update Julia code in a live session, so you'd have to quit your Julia session, modify your code, relaunch it, and all that. And so I think that's why it fell into disuse eventually. The next really big event in the debugging landscape was due to the amazing Kano Fisher, and he started a package called Gallium. And that package has, you can see the fingerprints of that package very much, and its descendants very much today. It introduced the syntax that we use for debugging. And Gallium targeted a very different level of that compilation pipeline. It was really, especially initially, aimed very much at the very lowest level of that compiler pipeline. So just to very briefly summarize kind of core principles of how Gallium worked, if it, the goal for implementing breakpoints, for example, was that what Gallium do was that it would take, if you wanted to insert a breakpoint in a function, it would take the compiled machine code that had been generated through all those stages of that pipeline and edit it in a way that would insert an interrupt that would essentially pause the CPU's execution of that code when it hit the breakpoint. And then what Gallium would have to do is it would have to figure out in this sort of essentially bit level data what every local variable's value was, and what line number you were in your code and all this kind of stuff, and then combine that with looking up all of the actual source code that had been supplied, and then weave all that together in a manner that would present it in a way that made sense to the actual programmer, okay? So this requires that you can span the full depth of that compilation pipeline, all the way between native code and up to what the user types, right? That has some huge advantages. One is the developer doesn't have to modify the code. Gallium does. It inserts those interrupts, right? But that's something that's easily reversible and you don't have to worry about. And the other huge advantage of this strategy is that the code runs at native speed until you start debugging, right? That's an enormous advantage. Unfortunately, as nice as that sounds, it did run into some obstacles. It turns out, maybe unsurprisingly, that traversing that many levels of compilation is an extremely difficult task, especially for a language that has so many abstractions like Julia. And it only barely works in languages that are, for instance, statically typed, and it's much, much harder in our circumstance. And so that, and supporting this across multiple CPU architectures and other things like that, made this a very demanding task. And then the fact that this needed a lot of work still to get working robustly, and the fact that Julia's internals were changing very rapidly at the time Gallium was being developed, meant that it got to a point where it wasn't very usable anymore. And so the package that we're talking about today is, its core is a package called JuliaInterpreter. It was built on a new effort by Kano to target a much higher level in the hierarchy and just stop there, which is the lowered code representation. And I'll tell you about that in a moment. And what we basically did was pick up this package, build on some work of others to update it to a modern form of Julia. We added a number of new features that are important, I think, for using it in many different types of applications. And we had, because we were trying to be more demanding and do everything in this package, this interpreter, we had to fix many corner cases of execution. And then we've worked somewhat on performance, and I'll tell you a little bit about some of these things. So the key thing, if you want to understand how this works, is to really understand lowered code. And while I've been involved with Julia for a long time, I really resisted for many years becoming familiar with lowered code. And I now regard that as a mistake, because it's actually quite easy to understand. You can sort of figure it out in an afternoon quite easily. You just have to sit down and actually decide to do it, basically. And so I'm going to give you a very, very quick demo. I'm not going to give you, by anything, a complete walkthrough, but just on an example function. So this is a function that just simply sums the values that are in an array. So it uses some of the simpler constructs that are available in Julia. And what we're going to do is we're going to pass this through Julia's lowering pass. And the lowering pass, I'm not going to read these, but you can. It does many things, and basically, if you want to boil down what lowering does, it takes the flexible, sophisticated language that has all these beautiful high-level constructs, and it turns it into a much simpler language, right? That's much closer to something like C or other languages like that. And so what it does is it basically reduces. Oh, okay, yeah. Very good. Awesome. So what it does is, it basically produces an equivalent set of code that's far simpler. And when you first look at lowered code, it looks daunting because it's filled with all of these kind of strange symbols. But with just a little bit of time invested, you can figure it out quite easily. So the key message is that there's really a pretty good correspondence between code you might write and then the code that's lowered. So for example, all these symbols here, like these %2s, these are local temporary variables that are defined by the line number they're created on. You have other temporary variables that are here. You see these hash numbers, but they just basically mark a block that you're about to jump to, to go down here. And so all that, well, I guess it's not wanting me to, oh, I guess here it is. That just means that you're going to jump down to this section of the code here. And so after a little while, you could learn to read this quite fluently. So what we did basically was write code and modify code that Kano had started that would let it essentially just go through that set of relatively small number of instructions and execute them, right? And so we had to do a few things, like we had to improve the ability to handle errors in code, because we were wanting it to be able to even run package level defining code. We had a lot of issues with scope and the world age and defining new structs and things like that. Things like LLVM call were particularly tricky to handle. And of course we had to implement breakpoints, which took us, I think, a couple of iterations to get something that was really flexible. And one of the key decisions we made early on was to try to stress test this by running Julia's own test suite. And to this day, we don't pass every element of the test suite, but we pass a remarkably large percentage of them. We also had to work on the performance because the compilers exist for a reason to make code faster. And so we learned a lot of sort of hard lessons in trying to make this run faster. So you have to really avoid internal dispatch within your own code. You also can't look up methods just by calling which every time you get to a function call in your code. And so we end up building a local method table for every single call in the lowered code so that we could have a shortcut to look up a much smaller number of possibilities. Dispatching to built-ins and intrinsics was another challenge that we had to figure out how to make a little faster. Handling C-call was a particularly big and complicated challenge in terms of making it efficient, and a fairly simple one, looking up the global names ahead of time. Performance is still not perfect. Many of you may know that very well, and we're happy to discuss that later on. I'm going to largely close by just simply sort of saying that many elements of JuliaInterpreter are not very complicated at all. It's not a huge package. If you have a bug or some way in which you want to make it better or are thinking about playing with performance, it's not rocket science in many areas. There are a few hard corners of it, but it's not terribly complicated. I think for what we're going to do next is mostly demos. I was going to show, well, I guess we may be running a little later than I wanted. I'm going to skip the Debugger demo just to give more time to the more sort of widely used packages, I think. So I'm going to turn this over to Kristoffer Carlsson, who's going to demonstrate debugger.jl.
Okay, so I'm going to present one of the sort of front ends to JuliaInterpreter, which is called Debugger. So we can just load it like that, and then I found some code on Rosetta code that computes the closest distance between two functions, so we just define it here. And the way we start debugging is we use this enter macro. So now we're inside a different REPL mode, which is called the Debugger REPL mode, and we can see the source code. We can see where we are right now in the source code. So right now we're at the top here. If we want to go one step down, we can use the end command. Now we're in line 3. We can examine the local state by examining the frame here. So I typed fr, and we can see that right now we have the variables p, n, and t available. We can also enter a Julia REPL like that, and now we can just query stuff about our local state. So if I write, for example, p here, I can see exactly what p is. I can even modify p. So something like that. And if we now look at our frame again, we can see that we updated our coordinate here. See where we are. We are at line 3. We can step another line. Now we're going to try to run get index here. And Tim talked about the lowered code. And we can also switch to have a view where we see the lowered code with a capital L. So now we can see exactly where we are here. We're at the get index call. If we want, we can step one step in the lowered code instead, so we can step an expression with SE. Now we're at the next get index call. We're at the minus. And now we're at the norm. So we're still at the same line, but we have stepped a few expressions there. So let's say we want to go into this norm call, then we can use S to step into it. Now we're inside linear algebra. Let's keep going. Let's step into this, norm 2. Now we're in here, and we're checking here if the length of our vector is smaller than a certain thing, then we use our own generic norm function. But if it's large enough, then we gain some performance to call out to BLAS. And we can take a look here what this norm 2 cutoff is. So apparently if the vector is larger than 32, then we call to BLAS. If we want to go back, we can step out of the function again. And now we're back to the top level. And one thing that's pretty useful when you're debugging is to insert this thing called watch expressions, which is some kind of expression that you want to see evolve over time. So let's say we want to check how these loop counters I and j change. Right now, they're not defined, so we're just going to get an undefined error. But I'm going to add a few variables we might want to look at. The min distance, that one is defined right now. So let's go into the loop so things are defined. Just press W to see all our expressions now. So right now, we're at the first outer loop here, I and j is 2. We have the minimum distance and the minimum points, and can step a couple of times. So we're at the next iteration of the loop. We can watch our expressions again, and now j is incremented by 1. And now if I would keep stepping by line like this, I would just go around in the loop a couple of times. But we also have another way of stepping by line with u, which is until, and then we will always go down. So if we're in a loop and it wraps back up, we'll just loop as much as needed. So I'm just going to run that to step down. Now we're outside of the loop. We can see the tuple is being formed. The return statement is executed. And that's the end of the function. So I think that there are more features here with the debugger, but in the interest of time, I'm just going to stop there and hand it over to Sebastian. Thank you.
Oh, yeah, here we go.
All right, cool. Juno, which some of you might be familiar with, is another front end, provides another front end for the debugger. It is also based on JuliaInterpreter, but completely separate from debugger.jl, which Kristoffer just showed. And in general, it is very similar. So you can enter the debugging experience with a Juno.enter macro, and this will give you many different UI elements and allow you to graphically step through your functions. So you have exactly the same options to step to the next line or step through an expression to the next expression, and so on and so forth. But one thing that Tim talked about already are breakpoints, and that's fairly easy to visualize and to activate in a graphical debugger. Those of you who have already used a debugger might be familiar with just clicking on a line number. We have something almost as good, which is clicking next to the line number. This will insert an unconditional breakpoint on this line, and all breakpoints are listed in this debugger pane on the side here. So if we continue the execution unconditionally, then we should end up at this breakpoint here. So let's try that. And indeed, we did end up here. The breakpoints can also be conditional breakpoints, if you're interested in that. So you can add click here, and this will allow you to add a condition to your breakpoint. So for example, if I want to break only when this loop variable, is equal to 2, we can do that. The color changes, and if we start debugging again, or even better, use the @run macro, which just runs all code in that macro expression in the interpreter, then we'll immediately end up at that breakpoint with I equals 2. So kind of similar to the watch expressions Kristoffer showed. In the workspace pane, you can look at all the different local variables that are defined. And indeed, we end up with I equals 2 for the conditional breakpoint. So that's just what we expected. Another thing that's fun to play around with is adding breakpoints for certain functions or methods. So if you want to add a breakpoint that will stop execution whenever we call norm, then you can type that in there, press enter, and you'll end up getting this breakpoint. You can also just add breakpoints for only certain methods if you're interested in that. But yeah, we can continue execution here, and we'll end up in norm, which is where this breakpoint was set. So yeah, that's just a short overview of what Juno can do and our debugger front ends can do. So I guess we're open for questions now.
So that is a fantastic presentation, guys. Debugging Julia on computers is amazing now. But there are these like Valentine and Tim black boxes. There's a Keno black box, so that way they take my code. It automatically goes to GPUs and TPUs. And now those might have slightly different, semantics or slightly different inner workings. And in theory, maybe, if we're generating code, I could put a breakpoint and you make a smaller GPU kernel and you let me look at it. Since you guys are masters at bringing theory to reality, right? Could the reality of automatically breakpointed GPU kernel accelerate, et cetera, is this something that is on your mind? And can I have it by next year?
Well, we have to write an interpreter for a TPU first, but yeah.
That sounds fun.
I mean, the problem with those things is that you really need to interact with the hardware there. You can't really write an interpreter, so it's quite a challenge. Yeah.
Could you have little parts go to the GPU?
we could write a really, really slow debugger on a GPU, one that would send a single instruction to the GPU and then come back, and then another and come back. Does that sound good? Yeah.
So one thing that the Julia interpreter reminds me of is Lua's JIT compiler, which has an interpreter mode available for, not only for debugging but also for faster startup. Mm-hmm. Is that a use case that the Julia interpreter allows too?
Okay, yeah, Absolutely, and they're actually already, so the Julia Interpreter has a macro at interpret, and you can put a function call behind that, and you're running it now in the interpreter rather than in compiled execution mode. And there are already use cases where you get going, considerably faster by interpreting the code than by compiling it first and then running it, of course, just on the first time, right? Then if you're rerunning the same thing again and again, I highly recommend compiling your code. I mean, there are still major performance issues with the interpreter, and I think for that to really start working well, we need to gain maybe at least one more order of magnitude on the interpreter. I'll be honest and say I'm not 100% certain about what the best strategy for doing that is that doesn't give something else that you want up, but there definitely are paths to go there. It's just a question, I think, of deciding what's going to be the best use of resources and give the best long-term outcome, really.
How does this compare with running Julia with -- compile equals min or compile equals no? I mean, you're interpreting it all in your package.
So this is actually something where I'll invite others to jump in and correct me, but it's very similar in some ways, right? So Julia itself has its own, interpreter written in C. If I remember correctly, and I haven't looked at it in quite a long time, if a method has already been compiled, that will still run the compiled version of it. So I think that we're actually fairly, in the tests that I've run, which are very few performance tests, we're fairly similar to the C compiler on the few performance tests that I've run, and we know for sure we're not running anything in compiled mode at all. So.
A newbie to Julia question. Convert from Python. Python's debugger has this marvelous construction: import PDB set trace. Is there an equivalent in Julia? So you set the breakpoint in your source code once, because what's the equivalent?
Yeah, you can just put in at BP, and that sets a breakpoint in your source code. So we have a macro to put in a breakpoint in your source code at a certain location, and if you interpret it, then it's going to stop there. I don't know if that.
What was it called again, please?
At BP, so short for breakpoint.
And we might also fairly soon have another macro you can just insert in a function call, and that function will be called, will be compiled and then called, so you can segment the performance penalties that come with interpreting code, but you'll still end up in a more or less interactive REPL session where you can inspect local variables and stuff like that.
Thanks a lot for the talk. Are there any plans to integrate the debugging infrastructure over top of the distributed computation side of the story, so that if you have different processes and you might have asynchronous errors, there's like a way to access where things happen and unwind all those stacks and trace them?
So that I think is actually much more of a doable task in terms of getting a decent result out of it than going straight for the GPU. So I'm not planning on working on it, and so this is definitely an area where any community contributions would be well appreciated. And we're very happy to help guide people through it. In some ways, actually, I don't think it would be that difficult of a task. You definitely have to put some time into it, but I don't think doing it in distributed computing is going to be horrible. Famous last words, right? So.
Okay, so I have a question for a single process running, and this is fantastic job, and you really have me bought, but I have not used it yet. But I know what typically problems I have, and I have two problems. First, can you step into a standard library function if you are using a precompiled binary? Because, for example, with edit, you cannot do it. And if you can do it with, this is fantastic then.
We have a thing to rewrite the standard library path so it works, yeah.
This is fantastic. And the second question is, how do you handle dynamically generated code? So if I have a dynamically generated code, so it's not in some file, how it shows like normally?
So, the guaranteed thing that works is if you inspect that. So it steps into it fine, has no problems, because it's working with the lowered code. And so since that's already been generated from the standpoint of lowered code, it's the same as everything else. The one thing that may not be available to you depending upon the package is a pretty printed expression there. So if you're willing to look at the lowered code, you have no problem. Debugger actually will show you the expression that was generated to create that function for you. So that's one little bell and whistle it has.
Okay, fantastic. Thank you.
Yeah. All right.
All right. So that's it for this talk. Next up, we're going to have our sponsor talk from Intel. So let's thank our speakers one last time.
No, the